Astrophysics is, above all else, a science of remote sensing. We cannot lower a thermometer into a star, nor scoop up a sample of a distant nebula. Almost everything we know of the temperatures, densities, compositions, and motions of the cosmos is reconstructed from light, and above all, from the sharp, discrete spectral lines that atoms imprint upon that light. A spectral line is the fingerprint of a quantum event, an electron inside an atom leaping between two discrete energy levels, absorbing or emitting a photon whose energy is exactly the gap between them. The line's wavelength names the atom and the transition, its strength counts how many atoms are poised to make it, and its shape records the temperature, the pressure, and the motion of the gas. To turn a spectrum back into physical conditions, we need three things: which energy levels an atom has, which leaps between them are allowed, and how a hot gas fills those levels and strips its atoms of electrons. The first two are quantum mechanics, the third is statistical mechanics. This chapter assembles all three. The history is a lesson in itself. In the 1880s, the Harvard College Observatory began photographing and classifying stellar spectra on an industrial scale, and one astronomer, Annie Jump Cannon, ultimately classified the spectra of more than 350,000 stars. By 1901 she had reorganized the old alphabetical scheme into the famous temperature-ordered sequence, OBAFGKM, and she did it empirically, purely from how the patterns of lines morphed smoothly from one class to the next, without yet knowing what physical quantity the sequence tracked. But why should a star's spectrum depend so overwhelmingly on temperature? And why, in particular, should the hydrogen lines that dominate the white A-type stars grow weaker in both hotter and cooler stars, when hydrogen is everywhere the commonest element? That remained a genuine mystery until the physics of excitation and ionization was placed on a firm statistical footing. The breakthrough came from two people. In 1920, the Indian physicist Meghnad Saha wrote down the equation governing how a gas ionizes as it heats, and in 1925, a young researcher named Cecilia Payne used Saha's theory in her doctoral thesis to prove two revolutionary things: that the whole spectral sequence is, at bottom, a temperature sequence, and that stars are made overwhelmingly of hydrogen and helium. This second conclusion so flatly contradicted the reigning belief that stars had roughly the composition of the Earth that she was pressured to dismiss it in her own thesis as probably spurious. Within a few years it was completely vindicated, and it is now textbook orthodoxy. The rest of this chapter retraces the path that Saha and Payne opened. It helps to be precise about what a spectrum is, and here the 19th century had already laid down the rules in the form of Kirchhoff's laws. A hot, dense, opaque body produces a smooth, continuous rainbow. A cooler, thinner gas lying in front of that source removes light at specific wavelengths, carving dark absorption lines into the continuum. And that same thin gas, viewed instead against a dark background, glows in bright emission lines at exactly those same wavelengths, because they arise from exactly the same atomic transitions. A star's spectrum is therefore a continuous rainbow welling up from the hot interior, crossed by a forest of dark absorption lines imprinted by the cooler gas of its outer layers. To decode the star is to decode those lines, so we begin with the atom, and with the simplest workable picture of it, Niels Bohr's 1913 model of hydrogen. Bohr supposed that the single electron could circle the proton only in certain allowed orbits, in which its angular momentum takes discrete quantized values. This assumption forces the electron's energy onto a discrete ladder of rungs, the lowest, the ground state, lying at minus 13.6 electron volts, and the higher rungs crowding closer and closer to zero, the threshold at which the electron breaks free. When the electron jumps between two rungs, it absorbs or emits a photon carrying exactly the energy difference, a relationship called the Rydberg formula. Jumps that end on the lowest rung form the Lyman series in the ultraviolet, those ending on the second rung form the Balmer series in visible light, the very lines that dominate optical spectroscopy, and those ending on the third form the Paschen series in the infrared. Bohr's model gets the numbers for hydrogen exactly right, yet it is conceptually wrong. Electrons do not trundle around in little classical orbits. The true framework arrived in the mid-1920s with the quantum mechanics of Schrödinger and Heisenberg, in which the electron is not a particle on a track, but a wave function, a three-dimensional cloud of probability. Solving its equation for the hydrogen atom reproduces Bohr's energy ladder exactly, but replaces the orbits with orbitals, those probability clouds of the s, p, and d shells. For atoms with many electrons, the energies can no longer be written down in closed form and must be computed on a machine, because every electron feels the nucleus and all the other electrons at once. But the essential architecture is universal, a discrete set of bound levels sitting below a continuum of free states. And it is precisely that architecture that produces line spectra. That architecture also gives us a clean picture of the three ways light and atoms interact. A bound-to-bound transition between two discrete levels makes a sharp spectral line, a bound-to-free transition, in which a photon with more than enough energy kicks the electron clean out into the continuum, makes an absorption edge, with smooth absorption beyond it. The Balmer jump seen in stellar spectra is exactly this, and a free-to-free transition, in which a passing free electron merely nudges a photon without being captured, adds a smooth background. Only the first of the three makes the discrete lines this chapter is chiefly about, but all three flow from the same quantized energy levels. To go further, we need to label the states more finely, and a bound electron turns out to be specified by 4 quantum numbers. The first, the principal number, mainly fixes the energy and the size of the orbital. The second fixes the shape of its angular momentum, the familiar s, p, d, and f subshells. The third fixes the orbital's orientation in space. And the fourth is spin, the electron's intrinsic, two-valued angular momentum. Over all of this presides the Pauli exclusion principle. No two electrons in an atom may share all 4 numbers. A single orbital, then, holds at most 2 electrons of opposite spin, and that one rule, applied shell by shell, builds the entire periodic table, and explains why every element carries its own distinctive structure of energy levels, and so its own distinctive spectral fingerprint. Not every possible leap between levels, however, makes a strong line. The most probable transitions, the ones that dominate ordinary spectra, obey a set of selection rules governing how the quantum numbers may change. Transitions that break those rules are called forbidden. They still happen, but only through far feebler mechanisms, so the levels they start from are extraordinarily long-lived or metastable. And here density enters. In a dense gas, an atom stranded in a metastable level is jostled out of it by a collision long before it can emit its forbidden photon, so forbidden lines are snuffed out. Only the near vacuum of a gaseous nebula or the thin interstellar medium can such an atom survive long enough to radiate, a fact that will return with great consequence at the end of this chapter. Knowing which levels exist and which transitions are allowed is still not enough. We must know how many atoms actually occupy each level in a hot gas, and that is a question for statistical mechanics. If the gas is in thermodynamic equilibrium at some temperature, so that collisions are frequent enough to balance every excitation against a de-excitation, then the relative populations of any 2 levels follow the Boltzmann distribution. Its heart is an exponential. The population of an upper level falls off as its energy above the lower level, divided by the temperature. In plain terms, a level lying high above the ground state stays almost empty until the thermal energy of the gas grows comparable to that height. A handy yardstick is that a thermal energy of 1 electron volt corresponds to a temperature of about 11,500 degrees. Take the crucial example of hydrogen. The Balmer absorption lines we see in visible starlight are made by atoms that are already sitting in the second level, absorbing a photon to climb higher still. So the question becomes, what fraction of hydrogen atoms occupy that second level? At the temperature of the Sun's surface, about 5,800 degrees, the answer is only about 5 in every billion. Raise the temperature to 10,000 degrees, and the fraction leaps to about 30 in every million, some 10,000 times greater. Taken by itself, then, the Boltzmann equation predicts that hotter stars should always show stronger hydrogen lines, and that flatly contradicts what we observe for the very hottest stars. The O and B types show weak hydrogen. A second piece of physics is missing. The missing piece is ionization. As a gas grows hotter, its collisions and photons do not merely lift electrons to higher rungs, eventually they tear the electrons off altogether. And once a hydrogen atom has been ionized down to a bare proton, it has no electron left at all and cannot make a Balmer line under any circumstances. The distribution of a gas across its successive stages of ionization, in equilibrium, is governed by the Saha equation, which Meghnad Saha derived in 1920 by treating ionization as a reversible chemical reaction, an atom in balance with an ion plus a freed electron. The Saha equation says that ionization climbs steeply as temperature rises, but, and this is crucial, that it falls as density rises. Buried in the equation is a term that counts the sheer number of places a freed electron can go, the quantum states available to it once it is loose. That term rewards ionization strongly at high temperature and low density, and the explicit appearance of the electron pressure carries a clear physical meaning. In a denser gas thick with free electrons, an ion recaptures an electron far more readily, so ionization is held back. This is exactly why a bloated giant star and a compact dwarf of the very same temperature show subtly different states of ionization in their spectra. And it is the basis of the luminosity class, the Roman numeral that accompanies a star's temperature type. Now comes the triumph, the moment the two pieces of physics are multiplied together. On one side, the Boltzmann factor gives the fraction of neutral hydrogen atoms that sit in the second level ready to make Balmer lines, and that fraction rises steeply with temperature. On the other side, the Saha factor gives the fraction of hydrogen that remains neutral at all rather than being ionized away, and that fraction falls steeply with temperature. The number of atoms that are both neutral and in the second level is the product of the two, negligibly small at low temperature because almost nothing is excited, rising to a sharp maximum, and then collapsing at high temperature because almost everything has been ionized, and that maximum falls near 9,900 degrees. It corresponds precisely to spectral type A0, exactly where the hydrogen Balmer lines are in fact observed to be strongest as they are in the spectrum of the bright star Vega. Below that peak, too few atoms are excited to the second level, above it too few atoms remain neutral to be excited at all. The strange, non-monotonic behavior that had baffled the classifiers of the 19th century, hydrogen strong in the middle of the sequence and weak at both ends, falls straight out of the two equations, with no fudging. It is one of the most satisfying calculations in all of astrophysics, and the very same reasoning applied element by element unlocks the entire spectral sequence. In the scorching O stars, hydrogen is almost wholly ionized and its lines are weak, while ionized helium shows through. In the B stars, neutral helium is strongest. In the A stars, hydrogen reaches its maximum. Through F and G, the temperature of our own sun, the lines of ionized and neutral metals strengthen above all the powerful H and K lines of ionized calcium. In the cooler K stars, neutral metals dominate, and in the coolest M stars, the spectrum is ruled by broad bands of molecules, notably titanium oxide, because at last the atmosphere is cold enough for molecules to form and survive. Every element's lines peak at the temperature where its own Boltzmann and Saha factors are jointly at their best. A word of honest caution is owed here. The Boltzmann and Saha equations assume thermodynamic equilibrium, a single temperature governing the velocities, the excitation and the ionization all at once, but a star is plainly not in global equilibrium. Energy is streaming outward, and the surface is far cooler than the core. The working compromise is called local thermodynamic equilibrium, the assumption that at each particular depth in the atmosphere, the matter is in balance with itself at the local temperature, even though the radiation streaming through it is not. Deep in the atmosphere, where collisions are ferociously frequent, this is an excellent approximation, but it can break down in exactly the thin outer layers where many of the lines we observe are actually formed. Collisions enforce equilibrium locally. Radiation does not, for a photon emitted in one place may be absorbed far away or escape the star entirely, and where the gas is thin, these radiative processes can outpace the collisions. When that happens, the level populations drift away from their Saha-Boltzmann values, and one must solve the far harder coupled problem of statistical equilibrium and radiation together. These corrections can shift an inferred abundance by a factor of 2 or more, so the two great equations are the indispensable foundation. They get the qualitative sequence exactly right and are reliable in the dense layers, but precision spectroscopy treats them as a first draft to be corrected, not the final word. This remains a live field of research. There is one more step from a line to a number. The strength of a line, measured by a quantity called its equivalent width, must be converted into an actual count of absorbing atoms, and that demands an understanding of the line's shape, which is set by 3 broadening mechanisms. The first is natural broadening. The uncertainty principle ties the finite lifetime of an excited level to an irreducible smearing of its energy, giving every line a small unavoidable width. The second is Doppler broadening. The atoms are in thermal motion, and their range of velocities along our line of sight shifts their absorption across a band of wavelengths, producing a bell-shaped profile whose width grows with the square root of the temperature divided by the atomic mass. The third mechanism is pressure broadening. Collisions with neighboring particles jostle the energy levels and blur the line, fattening its outer wings. Because this effect scales with density, the pressure-broadened wings of hydrogen's Balmer lines are a sensitive gauge of the surface gravity of a star, and, hence of its luminosity. A compact dwarf with its dense high-gravity atmosphere shows broad Balmer wings, a vast tenuous supergiant shows narrow ones. The full observed profile is a marriage of the two shapes, a bell-shaped thermal core with broad collisional wings, known as a Voigt profile. The final bridge from a measured line strength to a chemical abundance is a relationship called the curve of growth, and it has three regimes. When a line is weak, its strength grows in simple proportion to the number of absorbing atoms, twice the atoms, twice the line. But once the core of the line saturates, going as black as it can, adding more atoms barely deepens it, and the strength crawls upward only very slowly. Then, for the very strongest lines, the damping wings take over, and the strength climbs once more, now as the square root of the number of atoms. By placing many lines of a single element, of differing intrinsic strengths, on this one master curve, an astronomer can read off the column of atoms and, from the curve's shape, recover the temperature and the pressure besides. Combined with the Saha Boltzmann bookkeeping, this yields the total abundance of the element, and it is the foundation of stellar chemistry and of galactic archaeology. Two further kinds of transition, both of them technically forbidden, are scientifically priceless precisely because of where they form. Consider first the forbidden lines of nebulae. Their upper levels are metastable, immensely long-lived. In any dense gas, the atom would be collisionally knocked out of the level before it could ever emit. But a gaseous nebula is so tenuous, so far below the critical density at which collisions win, that the atom finally does radiate, producing bright forbidden lines, conventionally written inside square brackets, the green doublet of doubly ionized oxygen, and the lines of nitrogen and sulfur. Their mere presence flags a low-density gas, and the ratios of their intensities serve as delicate thermometers and density gauges for glowing nebulae. Before the atomic physics was understood, one of these green lines was blamed on a hypothetical new element christened nebulium, until, in 1927, it was shown to be nothing but forbidden oxygen. And then there is the most celebrated forbidden line of all, the 21-centimeter line of hydrogen. The ground state of a neutral hydrogen atom is split, ever so slightly, into two levels by the faint magnetic interaction between the spin of its electron and the spin of its proton. The tiny spin-flip transition between those two levels emits a radio photon with a wavelength of 21 centimeters. The transition is so profoundly improbable that a single isolated atom would wait, on average, some 11 million years to make it. No laboratory on Earth could ever detect it. But the galaxy holds such a staggering quantity of hydrogen that the integrated glow of all those rare emissions is easily heard. Predicted in 1944 and first detected in 1951, the 21-centimeter line became a cornerstone of radio astronomy, and for one decisive reason. Unlike visible light, it passes clean through the interstellar dust that shrouds the galaxy, and so it maps the cold hydrogen everywhere across the Milky Way and beyond, tracing out the spiral arms and, through its Doppler shifts, measuring how the galaxies turn. And it was exactly those rotation measurements, made in 21-centimeter hydrogen, that revealed the flat rotation curves of galaxies, one of the principal pieces of evidence for the existence of dark matter. Redshifted from the early universe, the same humble line is now being pursued as a probe of the cosmic dawn, when the first stars lit up, a frontier still uncertain, and one of the great quests of present-day astronomy, and so the loop closes on itself, from the quantized energy levels of a single atom through the statistical partitioning of a vast ensemble of atoms across their states of excitation and ionization, to the formation and the broadening of the lines themselves. The atomic and quantum foundations built up in this chapter are precisely what allow astronomers to turn faint pinpricks of light into temperatures, densities, compositions, and motions right across the universe. A spectral line is nothing more than a single electron falling between two rungs of a quantum ladder. It is also the alphabet in which the cosmos writes down its secrets, and we have in this chapter learned at last how to read it.